Okay, this is going to be the first of two videos on how to use calculus techniques to sketch the graphs of functions. And I think when we finish this process, most students are pretty surprised by how accurate these sketches are going to be. Now, when you start this, I'd suggest that you actually have two pieces of paper in front of you. The first piece of the paper will look like this. It'll have all the work with a series of steps on it. And secondly, you'll need a piece of graph paper. So I'd suggest just starting with a basic piece of graph paper, and we'll, as we do the work on the first sheet, we'll sketch the graph on the second sheet. Now, the technique that I use to do these things involves actually three processes. The overall plan will be to do this. First of all, we'll use the first derivative information, we'll use second derivative information, and then we'll sketch a few specific points, and then that should give you enough to make a final, very accurate sketch of the graph. Now, my technique on these is to do this. The first derivative is going to give you information about critical points, maximums and minimums, and where the function is increasing or decreasing. And what I like to do is to put that information, and I kind of use colors on this, I put them in blue at the top of the graph. So when I start these problems, I like to come up and I'm just going to put first derivative on this one right here. So the blue at the top of the graph is going to contain the first derivative information. So first derivative in blue at the top of the graph. Then, for the second derivative information, the second derivative is going to contain things like inflection points and where the graph's concave up or concave down. And I like to put that in red at the bottom of the graph. So I think I'll just go ahead and do that right now. We'll call this second derivative. So all the second derivative information will go in red at the bottom of the graph. And then we'll combine those two to get a final sketch. So it looks like that. So there's a starting point. Now, as far as the steps go, let's go back to our steps here. And there's 11 steps altogether. And before we get started, I just tell all my students the basic thing in these things is just be slow and steady. Yeah, don't get in a rush. And also, you're going to get a pretty accurate graph, so make sure you're not sloppy as you sketch the points and sketch the graphs, and you'll be surprised how accurate the final thing looks. Okay, now in this first thing, the first step on both these techniques is this, here's our original function, f of x is equal to 3x to the fourth minus 4x cubed. And it says this, on all techniques, first of all, if there happen to be any vertical or horizontal asymptotes, sketch those in the original function. Well, on this first example, this is a polynomial, and polynomials don't have any asymptotes. So right away, we can just do this. We can just say on this very first step, there are no asymptotes, so we can put none. So if you're working with a polynomial, the first step's actually pretty easy. There are no asymptotes. And we'll continue as we go down this. Now again, the idea is to build up a few specific points and then also use intervals to determine things like increasing, decreasing, and concave up. So as far as specific points to do, one that I generally put on there, a couple of them are going to be pretty easy. Plotting the y-intercept, that will give you a specific point. And again, to plot the y-intercept occurs where x is equal to 0, so all you have to do is define, set y equal to, and again, this is going to be the y-intercept. So to find the y-intercept, just set x equal to 0. So y would be equal to 3, and just in place of x, put a 0. And you've got minus 4 times 0 cubed. Of course, both those are 0, so you get y is equal to 0, and that's actually the y-intercept is equal to 0, which would be the point, actually, 0, 0. So we can go ahead and plot that in the graph, and what we'll do is, as we get specific points, we'll plot them. So I'll go over to the graph, and again, I'm going to go ahead and put that in blue here. So I've got the point 0, 0. So there is our first specific point on the graph. Now, back to the work again. So if we go back over here, now I want to get the x-intercepts. To get the x-intercept, you set y equal to 0. So we'll put that right here, say, here is the x-intercept. So to get the x-intercept, set y equal to 0 and solve for x. And sometimes this is easy and sometimes it's not. If it's something complicated, I'll just leave it off because it's just a sketch of the graph anyway. So to do this thing, first of all, let's go ahead and factor out an x. So I can make this be x cubed times 3x minus 4. Now, if this thing's equal to 0, either this factor is equal to 0 or this factor is equal to 0. This one gives you x is equal to 0. There is one x-intercept. And this one gives you 3x minus 4 is equal to 0. So that's going to give you x is equal to, if you move the 4 over and divide by 3, you would get 4/3. And sometimes it's better to put these things in, since you're going to plot them on a graph, change them into a decimal. So about 1.33. So there is the second. So I've got two x-intercepts. So now let's go put those on the graph. So let's go back to the graph. And the first one was x is equal to 0. Now we've already got that. Turns out the x-intercept and the y-intercept are the same thing. But you've also got about 1.33. So here's 1.3. 1.33 would be about right there. So we'll put, there's the second one. So now you've got the first couple of specific points on your graph, the intercepts. So back to the work again. Okay, now the next thing we'd like to do is this. Before we get finished, we're going to need the first and second derivative information. So we might as well go ahead and find those right now. And what I'll usually do is to find the first derivative, starting with the function. If the original function is f of x is equal to 3x to the 4th minus 4x cubed. So let's go ahead and find the first derivative. So f prime of x, and just using the power rule, that's going to be 12x cubed minus 12x squared. Now, that is the first derivative, but as you'll see when you find things like increasing and decreasing, a lot of times it's easier if you put this into a factored form. So I'm also going to write it in factored form like this. I can factor out a 12. I can factor out an x squared, and that's going to leave me with an x minus 1. So this is also the first derivative, but it's in factored form. Okay, now let's get the second derivative. So what the second derivative would be, it's just going to be the derivative of the derivative. So the second derivative, and again, starting with this one, using the power rule again, you would have 36x squared minus 24x. So that is the second derivative. Now again, as far as determining things like concave up and concave down, it'll be easy to work with these things in factored form, so let's go ahead and factor this one too. So out of this one, I can factor out a 12x, and that's going to leave me with a 3x minus 2. So 3x minus 2. So again, when I do these, I find it's generally easier to work with a factored form of the derivative. So you've got first and second derivative out of the way. Okay, now what we'd like to do is, in the next step is, we want to begin to identify intervals. Intervals for where the graph is increasing or decreasing. Try to find critical points, try to find maximum, minimum, and that's all first derivative information. So I think I'll start by just writing the first derivative down again, and I'm going to write it in this factored form. So I know that f prime, so the first derivative in factored form is 12x squared times x minus 1. So there's first derivative in factored form. Now again, as far as critical points go, critical points are where the first derivative is either equal to 0 or is undefined. So let's start by finding, let's set the first derivative equal to 0 and solve for x, and that's going to give you your critical points. So I've got x minus 1. Now I'll set each factor equal to 0, that one equal to 0, and that one equal to 0. When I set x squared equals 0, it gives me x is equal to 0. So there is one critical point. And then I've got x minus 1 is equal to 0. And I get x is equal to 1. And there is a second critical point. So I've got two critical points. But I actually have to mark these critical points on the graph. So I've got the x value, but I don't know what the y value is. So to find the y value, I'll evaluate the original function at x equals 0 and x equals 1, and that will give me the y values for the critical points. So I want to go to the original function. I'll find f at 0. Now the original function was 3x to the 4th, and we'll plug in at 0, minus 4x cubed, and again we'll plug in at 0 and solve for y. So this gives us f at 0 is equal to, this will turn out to be 0. So when x is equal to 0, y is equal to 0. That gives you the point 0, 0, and that is your first critical point. Now to find the y value of the second one, go to the original function, and this time plug in a 1. So this would be 3 times 1 to the 4th minus 4 times 1 cubed. So when x is equal to 1, this would turn out to be 3 minus 4, which would be a negative 1, and that gives you the point 1 and negative 1, and that is the second critical point. So you've got two critical points. One of them occurs at 0, 0. One of them occurs at 1, negative 1. Now, as we find things, we'll go ahead and plot them on the graph. So every time you determine something, let's go ahead and put that on the graph. Now again, this is first derivative information stuff, and it's going to be in blue. So we go back to the graph. Let's go to here, and we want to plot the point 0, 0. Now in this case, as it turns out, the y-intercept and the x-intercept, both of them, it turns out to be a critical point. So I'm going to put a little CP right here for critical point. Now the second one, it was 1 and a negative 1, which puts it right there. So that is also going to be a critical point. Now another thing that I like to do here is this. This will help you when you sketch the graph. What a critical point is where the first derivative is equal to 0. Well, the first derivative is the slope of the tangent line, which means the slope of the tangent line is 0 here. So that means you have a horizontal tangent. And you'll find it's going to help your graph sketching if you come in and actually draw yourself a short horizontal tangent right through those points. So it's going to look like that. So right now, you know you have a critical point. And actually, let's do one thing here. You can have some possibilities. At a critical point, it could be a maximum, it could be a minimum, or it could be neither. So it's possible the graph could come down like this and then go up like this and be a minimum. It's possible the graph could come up like this and then go down like this and be a maximum. Or it might do something like this. It could go up, level off at a horizontal tangent, and then go up again and be neither. So the question is, do you have a maximum or a minimum at these critical points? And also, what intervals do we have? So we've got the critical points plotted. Let's go back to our work. Now what the work says is it's mark the critical points on the graph, which is what we've done. But it also says, and this is one of the most important things, mark the corresponding intervals on the graph. So the critical points break the graph up into intervals where it might be increasing or decreasing. So let's go ahead and put those on our graph. And again, I always do these things in blue. So what happens, I've got a critical point here. So I'm going to draw in blue a vertical line it's going to go right through that critical point. So I come up to here and go down to here, and I'll draw a vertical blue line right there. So there's one dividing point on the intervals. Another critical point's here. So again, I'll come up to right here. I'll go down to here, and I'll draw a vertical line in there. Now what that does, that divides the graph up into 3 intervals. Now let's go ahead, and I like to mark these at the top of the graph. So I'm going to go up here and go from here to here. And here's the first interval. It goes from negative infinity to 0. I've got another interval that goes from here, say, to here. So again, I'll put that up here in blue. And it goes from 0 to 1. And finally, the third interval goes from here off to a positive infinity. And it looks like that. So the critical points divide the graph up into 3 intervals, and the question is what's going on inside each one of these intervals. Is the graph increasing or decreasing? And to do that, you might remember, if you evaluate the first derivative and the first derivative is positive, then the graph is increasing in the interval. If you pick a test point and evaluate the first derivative and it turns out to be negative, then it's decreasing. So let's go back to our thing. We've found the critical points, and let the critical points divide the graph up into intervals. So back to the graph. And the next one says this. Now you want to find out, is it increasing or decreasing each one of those intervals? So the idea is pick yourself a convenient test point inside each interval Evaluate the first derivative at that test point and see if it's positive or negative. If it's positive, the function's increasing. If it's negative, the function's decreasing. So back to our graph again. So what we want to do is to figure out which test points to pick. And again, my suggestion is try to pick the easiest possible test point. Pick an integer if you can. So in this interval, I'm going to pick -1 because it's easy. In this interval, I think I'll pick 0.5. I can't pick an integer in this interval, so I'll pick 0.5. And then in this interval, I'm going to pick 2 just because it's easy. So I'm going to pick -1, 0.5, and 2. Those are going to be my test points inside the interval. Now, if you wanted to, you could pick -2. You could pick anything you want to as long as it's inside the interval. So let's do that. So we go over and we're going to evaluate the first derivative. And this is going to be, again, we'll stay in black here. This is going to be the first derivative evaluated at -1. Then we're going to have the first derivative evaluated at 0.5. Then we're going to have the first derivative evaluated at 2. And all you're interested in here, you don't care about the numerical value. You only want to know, is it positive or negative? Now, this is where it's particularly handy to use that factored form of the derivative. Let's go back up and look at that. So we found the first derivative. You could use this form if you want to, but I think it's actually easier if you use this factored form. So 12x squared times x minus 1. So I'll go ahead and write that right here just one more time. So the first derivative is 12x squared times x minus 1. Now, I sort of use a shorthand notation on this. This is going to be 12. In place of the x, I'll plug in a -1 squared times -1 minus 1. And all I want to know is this thing positive or negative? Well, I've got the 12, so I'll write that right there. Then I do this. Without worrying about the numbers, if I take any number and square it, it's going to be positive. Then -1 is a -2, but all I care about is that it is negative. Now, when you multiply these together, a positive times a negative is a negative, which means that in this interval, the first derivative is negative. And what that means is that the graph is decreasing. So it's decreasing in the first interval. Now let's figure out what's going on in the second interval. I've got 12, plug in a 0.5 squared times 0.5 minus 1. Now we'll use the same technique again. This is going to be 12. If I take a positive number and square it, I get a positive number. Actually, just positive. We'll make that one just be strictly positive. Then 0.5 minus 1 would be a negative 0.5, but all I care about is the fact that it is negative. So positive times a negative, that's going to be negative. In this second interval, the first derivative is also negative, which tells you in the second interval, it is also decreasing. So now what's going on in the third interval? So we'll take 12, plug in a 2, squared, times 2 minus 1. So there's the 12. Now, when you take a 2 and square it, you'll get a positive. 2 minus 1 would be a 1, but all I care about is that it is positive. So everything there is positive. When you multiply those together, you will get a positive. So the first derivative at 2 turns out to be positive, which tells you that the graph is increasing. So now, in the first interval, it's decreasing. The second interval, it's decreasing. The third interval, it's decreasing. So now go to your graph and put that information on the graph. So we'll go over here. Let's go to the first derivative. I know in this first interval here, it's decreasing, and I like to write that in blue at the top of the graph. In the second interval, it's also decreasing, so I'll put that right there. And finally, in the third interval, I know that it's increasing. So right now, you're learning a lot about your graph. You know where it's increasing, decreasing, and so on. Now, the next thing you'd like to know is you've got critical points, but you want to know at these critical points, do you have a maximum, a minimum, or neither? And again, let's go back to our work and see what we've got on this, see what the next step is. So the next step says this. Use the first derivative test to determine if each critical point is a maximum or minimum or neither. Now, if it's been a while since you've done the first derivative test, let's take a quick look just to see what that is. So what the first derivative test says is following. in the first derivative. If you have a critical point, if the derivative changes from positive to negative, in other words, if it goes from increasing to decreasing, you have a relative maximum. If it goes from decreasing to increasing, then you have a relative minimum. And finally, if at a critical point, the derivative does not change signs, then that tells you that that critical point is neither a maximum or a minimum. So it would be neither. Okay, so now back to our steps. And we'll drop back down to this first derivative test. And actually, to do this, you can just look up at the previous step. So what happens, and let's go ahead and I think we'll do this one in blue. We went from decreasing to decreasing. It did not change signs. So this tells you that the first critical point is neither. It's not a maximum or a minimum. In the second interval, it went from decreasing to increasing. So if it was going down, now it's coming back up again. This has to be a minimum. So what this tells you is that the first CP, first critical point, is neither, not a maximum or a minimum. Then you know that the second critical point, because it went from decreasing to increasing, has to be a minimum. And I would suggest write that information on your graph. So again, we'll go back to the graph, and every time you learn something, putting it on the graph. So what you learned here is this first critical point was neither. It's not going to be a maximum or a minimum, so I'll write that right on the graph. I also know that this critical point turned out to be a minimum, so when I sketch my graph, I know I'm going to have a minimum right here. So you're learning a lot about your graph already. You probably have a rough idea about what this thing's going to look like. But right now, you only know increasing or decreasing. What you'd also like to know is concave up and concave down. And we'll use the second derivative in inflection points to describe the concavity of this graph. So right now at this point, we're done with the first derivative information, and we'll switch to concentrating on second derivative information. So back to the work again. Okay, now just a reminder, the inflection points occur where either the first derivative is equal to 0 or the first derivative is undefined. So what we'll do is take the second derivative. We'll take the second derivative, set it equal to 0, and use that to find the inflection points. Now, just a reminder of what each one of these things are. Let's just write it down here again. The second derivative, and again, it's probably going to be easier to work with it in factored form. So the second derivative, and you can look back up at a previous step up here. The second derivative is 12x times 3x squared minus 2. So we'll go down to here. And I've got 12x times 3x, or 3x minus 2. So there's the derivative. So what I'd like to know now is where this thing's equal to 0. So I'll take the second derivative and set it equal to 0. That's going to be 12x times 3x minus 2. Now, if this thing's equal to 0, either this factor is equal to 0 or this factor is equal to 0. So this one is going to give you x is equal to 0. Now what that is one possible inflection point. So there's one possible IP. Now remember, it's not actually an inflection point unless the concavity changes. So at this point, the best you can do is identify possible inflection points. So let's set the second factor equal to 0. And if you solve for this, you would get x would be equal to, move the 2 over, this would be 2/3. And again, because we're plotting graphs, it's probably going to be easy if you go ahead and change that to a decimal. So that'd be about 0.66. So there is the second possible inflection point. So now I know the x values of the points, but I also need the y values to be able to plot them. So to find the y values of the inflection point, take these two x values and plug them into the original function. So first of all, your first one would be f at 0. And we've actually done this in a previous step. This would be 3 times 0 to the 4th minus 4 times 0 cubed. So you get 0 cubed. Of course, that's going to give you 0. F at 0 is equal to 0, which gives you the point 0, 0. And that's going to be an inflection point. Now, as it turns out, that's actually the same thing as one of the critical points. Let's go ahead and look at the graph real quick on that one. So if you wanted to plot that, you got the point 0, 0. Now again, this is second derivative information, so we'll plot all the second derivative stuff in red. Now, I've got the point 0, 0, and since it's the same one, I like to do this. I'm going to put a little circle around this thing in red. So the point 0, 0 is both a critical point, and it turns out it's also a possible inflection point. So let's put it right there. So that takes care of that one. So now back to our work. And let's find the second. If x is equal to 2/3, what's y? So evaluate the original function at 2/3 would be 3 times 2/3 to the 4th power minus 4 times 2/3 cubed. And that's going to give you f at 2/3 would be equal to, and if you stick that on a calculator, it'll turn out to be about 0.60. So what this gives you is the point when x is equal to 0.6, y is equal to 0.60, and that gives you the second possible inflection point. So there was the first possible inflection point. Here's the second possible inflection point. So go ahead and plot this one on the graph too. That way you'll have both your inflection points. And again, this is second derivative information, so we'll plot it in red. So when x is equal to 0.66, which would be about right here, y was equal to 0.6, which would be about right there. So you'll wind up with and try to be pretty accurate with this, it'd be about right there. So there is a second possible inflection point. So back to the worksheet. Now back in the worksheet, it says this. We mark the points on the graph, and just like we use the first derivative to divide the graph up into intervals where it's increasing or decreasing, we'll use the second derivative to divide the graph up into places where it's concave up and concave down. So again, it would change concavity at the inflection points. So everywhere you have an inflection point, go ahead and draw a vertical red line, which will divide the graph up into those. So let's do that. So again, when we're working with first derivative information, we use blue lines. This time we use red. So this time I'm going to put a vertical red line through each inflection point. So I'm going to go from here up to here, and it'll be right there. Then I'll go from here, about right here, up to here and draw one in through here. Okay, so there are my intervals. Now that's going to divide it up into intervals. So I'm actually going to go ahead and when I work with the first derivative, I put it in blue. When I work with the second derivative, I'll put it at the bottom of the graph in red. So I'm going to go from here to here. Here's the first interval. And that goes from -infinity to 0. Then I've got a second interval that goes from here to here. And that goes from 0 to 0.66. And then I've actually got a third interval that goes from here off to a positive infinity. And it looks like that. So there's the third interval. So now that divides it up into 3 intervals. And the second derivative will tell you about concavity. So when I worked with the first derivative, it gave me increasing and decreasing. In these red intervals, we'll put what we know about concavity. So back to the worksheet. Okay, now let's go down. And again, exactly like we did when we found increasing and decreasing, if you want to find about concavity, pick a test point inside each interval. And again, I want to emphasize a convenient test point inside each interval and find out if the second derivative is positive or negative. And just a reminder, if the second derivative is positive at your test point, it's concave up. If the second derivative is negative at your test point, it's concave down. So let's figure out what's going on in each one of these intervals. So to figure out which test points to pick, go back to the graph and just pick a convenient test point. And I suggest work with an integer if you can. So again, in this first red interval here, I'm going to pick -1 just because it's easy. In this second red interval, just to be different, I think I'll pick 0.1 this time. I can't pick an integer, so 0.1 is an easy number to work with. And finally, in this third interval, again, I'll pick an easy number, and you can pick 1 if you wanted to, or you can pick a critical, as long as it's in this red interval, so I think I'll pick 1. So what I'm going to have is -1, 0.1, and 1 will be my 3 test points. So back to this graph. So I'm going to evaluate the second derivative. So the second derivative evaluated at -1, Then I'll have the second derivative evaluated at 0.1. And I'll have the second derivative evaluated at 1. Because each of those is a point inside the interval. And we'll do the same thing we did before. Let's look up and find the factored form of the second derivative. And that would be this. So you've got f prime prime of x. And it was 12x times 3x minus 2. So that was the derivative. So we plug these things in. This is going to be 12 times, and in place of x, I'll put a minus 1. Then this is going to be 3 times a minus 1 minus 2. Okay, that's going to give me 12. This second one is going to be negative. And the third one, again, I'm not interested in the numerical value. I just want to know, is it positive or negative? So that's going to be minus 3 minus 2, which would be a minus 5, but that's also going to be negative. So two negatives make a positive. This whole thing will turn out to be a positive. So it's going to be positive. And what that tells me is, again, if the second derivative is positive, it's concave up. So I'll put a little CU right here. It's going to be concave up in this first interval. Now the second interval. 12 times 0.1, and I've got 3 times 0.1 minus 2, and that's going to give me, this will be 12. 0.1 is positive, and this would be 0.3 minus 2, which would be a negative. When I multiply those together, I would come up with a negative. In the second interval, the second derivative is negative, which tells me that it is concave down. Now the third interval. So 12 times 1, and you've got 3 times 1 minus 2, which gives you 12 times, and again, 1 is positive, and 3 minus 2 would be 1, which is also positive. Everything in there is positive. When you multiply them together, you would get a positive. So that's going to be positive, which tells you that in this interval, it is concave up. So now let's go ahead and write that information on the graph. So every time you determine something, go ahead and put it on your graph. So we go back to the graph. And again, this is second derivative information, so we'll put it in red. So in the first interval, I got that it was concave up. So I like to put a little CU right down here. In this second interval, in here, it is concave down, so I'll put a CD. And finally, in the third interval, it's back to concave up again, so I'll put a CU. And notice, we haven't actually drawn anything on the graph yet, but you've learned a lot of information about your graph so far. So let's go back and see what the next step is. Okay. Now in the next step, and actually we're getting very close to the end now, these are the last two steps. You want to find the end behavior of the graph. So what that means is what happens as the graph goes way off to the left, so as x approaches negative infinity, what happens as the graph goes way off to the left, and what happens as the graph goes way off to the right. And this is actually just like taking limits in infinity, so let's start with the function. So the original function was 3x to the fourth minus 4x cubed. Now, remember, whenever you take the limit at infinity, you have a dominant term. X to the fourth is the dominant term, so really you can forget about this term. This thing will turn into 3, and I'm just going to go ahead and put a large number in there, if you substitute a large number. So, a large number to the fourth is just a large number, and 3 times a large number is a large number, which it goes off to, in this case, it turned out to be positive infinity. Now, what this means is, as x goes way off to the left, y is going up to a positive infinity. So the important thing is that this graph is going to finish by going up. Now let's figure out what's going to happen as you go way off to the right. And again, 3x to the fourth. Oops, I'm sorry. When I did this, each one of these should have been a negative infinity. So if I take a negative infinity to the fourth power, that's going to be a positive. It looks like this. So this will begin 3x to the fourth minus 4x cubed. So this time I'll put in a positive large number. So this will be a positive infinity. And again, this is the dominant term, so you don't have to worry about this term. This would be to the fourth, which would be a large number to the fourth power is just a large number. and 3 times a large number is a large number. So this one also turns out to be a positive infinity. So again, as you go way off to the left, to the right, this time, this one also goes up. So the end behavior of the graph is that both graphs have y going up toward a positive infinity. And now that really takes care of all the information that we needed, except for one thing. Finally, use all the information on your graph to sketch it. So let's go and finally put all that work to use. So back to the graph. Now, on the graph, we're going to do the following. I want to sketch it. But let me show you a way to sketch it wrong to start with. I always get a few students that do this. Now, you put a lot of work in to try to get an accurate graph, and it'd be a shame to blow it right here at the end. So some students, initially, they'll do this. They'll go, it's decreasing, and it has to go through this point. So they'll draw a graph that looks maybe something like this. I'll show it. Well, this graph is decreasing. It goes through this point, and that's good. But the trouble is, that's not good at all. That's horrible. You didn't follow all your information. So if you did this, here's the problem with this, is that first of all, it has to be concave up in this interval. And I like to use these little hairs to indicate things, but that would be concave down. The little hairs are on the bottom of the graph. So if I did it this way, it's actually concave down. So it can't possibly look like that. Now also, as it comes to this inflection point, it's a critical point. It has a horizontal tangent. So the graph has to level off at a horizontal tangent here. In other words, it has to look more like this. It has to go from here and level off. There has to be a horizontal tangent right in there. And if you don't draw that horizontal tangent, you'll get it wrong. So when you draw it, it'll actually look something like this. This graph would be concave up, levels off at a horizontal tangent, and does this. So make sure when you sketch the final graph that you do it accurately. Otherwise, you really just kind of wasted all your time here. So let's get rid of this, and we'll try it one more time. And this time, we'll sketch our graph and concentrate on being accurate as we go through this thing. Okay, so let's sketch the final graph now and try to make it really accurate. So to do this, what the idea is to, in each interval, look at the top and the bottom and see what you've got. So in this first interval, we need a graph that's decreasing and concave up, and that hits a horizontal tangent right here. So what I'm going to do is, starting right here, I'm going to go ahead and draw. It's got to come off with a horizontal tangent here. It's got to be decreasing as I go this way. So it has to be decreasing, and it also has to be concave up. And it's a little tricky sketching these, but I'll just put a fairly rough sketch in, but I want to get it reasonably accurate as I go through this thing too. So it's got to look something like that. Now, I like to put these little hairs on the graph. And if it's concave, this indicates concavity. If it's concave up, I put the little hairs on the top of the graph. If it's concave down, I put the little hairs on the bottom of the graph. And this just helps me to visualize concavity. So it's going to be concave up. It levels off to a horizontal tangent. It goes through and it hits the point right there. So in this interval, it has to be decreasing, which it is, and it has to be concave up, which it is. So now what's going on in the second interval? In the second interval, it has to be decreasing, but it switches to concave down. So it has to be going down and also curving down, and it has to, again, come off a horizontal tangent right here. So the horizontal tangent would look something like this. It's got to be curving down because it's concave down, and it has to be decreasing to this point. So it's got to look like that, and again, I'll put little hairs this time to indicate that it is concave down in this interval. And that's true until it gets to this inflection point right here. So again, make sure that it's decreasing and concave down. Now, the third interval, what happens in this little interval in here? On here, it's decreasing, but it switches to concave up. And it has to hit a horizontal tangent right here. So it has to be decreasing, concave up, and level off at a horizontal tangent right in here. So it's got to look something like this. It has to hit a horizontal tangent. Switch to concave up, and went through this point right here. So now in the fourth interval, it switches to increasing. It's got to be concave up, but you add one extra thing too. This is the x-intercept. It has to go through that point. So starting from here, start with it, level off at a horizontal tangent. It switches to concave up. It goes through that point, and it continues up like this. Now at this point, it's got to continue increasing, and it has to continue concave up. So it has to look something like that right there. Now again, I'll put the little hairs to indicate that it's concave up in this entire interval. So it's got to look kind of like that if I go through this. And I'll continue putting these things on up here. And really, that's pretty much what the graph is going to look like. Now, the last thing is endpoint behavior. And just a reminder, let's go back to our sketch over to our worksheet here. If you go way off to the left, this thing goes, y goes up toward a positive infinity. So it was a positive infinity here. If you went way off to the right, it was also positive infinity. So in both cases, it went up. And let's see how that works with our graph. So sure enough, if you go way off to the left, I'd like to put an arrowhead out here. And so the end behavior is that this thing continues going up. This one also continues going up. Now, occasionally I get a few students that'll say this, and it's a good question. They'll say, well, how do you know it doesn't curve back down again? How do you know it doesn't do something like this? Maybe it goes from here, and it goes back, and it goes back down again. Well, it can't do that, and the reason it can't do that is if it did this, then you would have another critical point right here with a horizontal tangent, and the end behavior would have it going down. So because there's no additional critical points, it can't curve back down. So we can go ahead and erase this, and you know that the graph has to look something like that. Now finally, the final question is, how accurate is this? So I went ahead and did this one on a computer. Let's put a computer-generated graph on top of this just to see how accurate we really were. And we'll do that in red. So this red graph is the actual graph you would get if you did it on a computer. And notice, it's extremely accurate. As a matter of fact, let's go ahead and turn off the black graph just for a second, and you'll see the red graph, if you did it, satisfied all our requirements. Horizontal tangents here, minimum here, concave up, concave down where it's supposed to be. The inflection points are where they're supposed to be. So let's put our graph back on there again. And you can tell if you do this right, you'll come up with an extremely accurate graph. So we'll turn off this thing one more time. Let's turn off the red graph. And let's take one last look at each individual part. When you're working with first derivative information stuff, let's turn off the second derivative stuff. So let's turn off all the red stuff. And sure enough, you'll see that the first derivative did exactly what it's supposed to do. It identified intervals where it's decreasing, then decreasing again, then increasing. It found the critical points, and it told you whether you had minimums, maximums, or neither. Now, when you got around to the second derivative stuff, that told you about concave up and concave down. So this time, let's turn off the first derivative stuff. So in this case, the second derivative gave you the inflection points, and it also told you it's concave up in this interval, concave down in this interval, and switches back to concave up in this interval. And then when you finally put both the blue stuff and the red stuff on the graph, it shows you all the intervals. And then if you sketch the final graph, you can get a really accurate final graph. So anyway, if you follow these steps, they'll pretty much guide you through this. And my suggestion is to delay the sketching of the final graph until you complete all the steps, and that will allow you to make an accurate graph. But again, be accurate where you have a horizontal tangent. Make sure the graph levels off and actually has a horizontal tangent. And make sure that it really is concave up or concave down where it's supposed to be. So what this is, this was an example of a graph, a function that did not have any asymptotes. Now, in the next video, we'll look at a function, a rational function that does have asymptotes. We'll use the same series of steps, but it'll change things just a little bit, but it'll be essentially the same process. So hopefully this helps you a little bit on using calculus to sketch accurate graphs.